Yes. There is no try. There is only do, young Padawan.
He's talking about your homework. Do it.
Yes.
But seriously, it's Monica.
And Milks.
And we're here with your last homework in the unit on the behavior of gases. So let's hit up the notes real quick so we have time for the calculations at the end. So KMT. It is a theory that Milk says it's got 5 postulates, but we're not going to hit all 5 of them up.
No, we're going to hit
about 3 major portions. The first being gases behave like small particles traveling in straight line motion. That's an assumption. We have to assume they behave like this all the time, or else these equations and calculations that we're going to use don't work.
Yep.
But
the other one is that they occupy no volume. Now, we know that that isn't true, but it's really close to being true. Let me explain real quick. Take all the gas in this room, shrink it down so all the molecules are touching. We're talking the size of a pea. Relate that to the volume of the whole room.
There's really
very minimal.
No gas molecules present. So anyways, that's not testable. The first postulate is there. Now, the last one is also testable. Collisions between molecules are perfectly elastic, meaning that when one gas molecule hits the wall of the container, it transfers all of its energy into the wall of the container or the other gas molecule. Nothing goes missing. In reality, this can be the
Not
case,
perfectly elastic.
but this is a theory and not necessarily a law.
And the theory helps us understand what we call an ideal gas, which makes it become very predictable. So that close to KMT means the closer I am to KMT, the more ideal my gas behaves.
Right. And the key term is like under which conditions does this gas behave like most ideally?
Right. So it must be hot.
Small molecules.
Small. Hydrogen and helium are much smaller than carbon dioxide.
The best ones to use as examples for KMT. They have to be at high temperature, so they're zipping around in straight lines.
Real fast, they don't feel each other.
And they have to be at low pressure, so there's lots of space in between them.
Not squishing them down so they're cramped up into a space.
We don't want these imaginary molecules of gases to actually get close enough so they stick together, because then they don't obey KMT and they're not behaving like an ideal gas.
We don't even want them to feel each other.
Now, there's 4 gas laws that went into making the combined gas laws. So let's
Correct.
give you a quick rundown of what they are.
All right, so first one is what's called Guy-Lussac's law. Okay, and it relates pressure and temperature, but at constant volume. So the volume here isn't going to change.
Confined. It's sealed up.
Right, so as the temperature increases, the pressure will increase.
If I were to heat this up, the pressure inside there, if there were a gauge, would increase.
Right,
If I were to
the
cool it
molecules
down,
start moving faster, bang harder. Come on, go ahead, Monica, go ahead. Right, and the opposite's true if I cool it.
Right, they go slower and slower and slower, and the pressure goes down. So this makes a direct relationship.
As one goes up, the other goes up.
Right, so
One goes down, the other.
temperature goes up, pressure goes up. Temperature goes down, pressure goes down. And it looks like a straight line on a graph.
Yep, and there it is.
There it is. The next law, Charles' law.
Okay, go ahead.
Charles is temperature versus pressure, constant pressure, temperature versus volume. So the pressure is staying the same, 1 atmosphere, but the volume and temperature are going to change. And how are they related?
Right.
Well, as I
Use a balloon analogy.
increase the temperature on a hot air balloon, the volume of the balloon expands and fills up. Eventually, it can carry people in a little basket underneath.
Right, and quite the opposite.
Right, as I decrease the temperature inside that balloon, a balloon will eventually shrink and shrink and shrink and go back down. To, that's how hot air balloons work.
Yep.
Right? You got to get back down to the ground, let it cool off, let some cold air in there.
Birthday balloons act exactly the same way.
Exactly. So it's another direct relationship, and it's another linear positive slope.
Yeah.
So as
You guys
volume
will need to
increases,
be able to
temperature.
figure out these relationships graphically. You will need to, if you can't memorize them, you will need to learn how to produce them. Okay.
Boyle's law.
Last one, and this is not boil as in water boils. We take volume and pressure, hold temperature constant now.
Yep.
So as the pressure goes up, the volume will go down. So the more I push,
Sealed container, the more pressure I push on the outside, the volume of the gas goes low. And the opposite's true. If I were able to stretch this, it would go up.
so now that's an inverse relationship, and I'm going to get a different looking line because we haven't had one of these yet. Pressure, volume, the relationship is going to look like that.
So the higher the pressure on the gas, the more squished the molecules get together,
More
the
pressure,
volume
push
goes
it.
down.
Right.
So when Mr. Milk said if I take all the gas in this room and compress it, it would be the size of a pea. That's the relationship we're talking about.
Push on it, right? There's space in there.
Now, there's one more law that governs the whole idea of what a mole is, and it's Avogadro's law.
Right. So the number of moles in a gas will be equal to the number of moles of another gas if the temperature is the same. That was the actual law we did last unit. We need to remember that 1 mole of gas is always 22.4 liters. More moles of gas, more volume.
Exactly. The more I pump on the tire pump, the more gas is going into my tires, the more moles of gas are in that tire.
Right. So
pressure will
Yep.
increase and all that other stuff.
So on table T, we take all these equations, we put them right together. We're not going to touch you too much on the rate loan equations. This is the one that's in the reference tables.
What you're going to have to do with these calculations, which is why we're trying to save some time for that, is you're going to be given 5 of the 6 variables. And you have
Yes.
to solve for the 6th variable using algebra.
Right. And know that the one is the initial conditions, the 2 is the final.
Because we're always comparing before versus after. We
Right.
know, so there we go.
Right. Some quick examples. We'll go through these real fast, right? Heating an aerosol can that's got a fixed volume. What's going to happen if I heat it up too much?
Pressure goes out through the roof, kaboom.
Boom. Cooling a balloon. I take my birthday balloon, put it outside. What's going to happen to it? It's going to shrink.
Because the volume's flexible.
Right. Air pressure is constant.
Right.
Okay. Engine cylinder.
As the cylinder rises towards the cylinder head, the pressure inside the cylinder increases until sparks, explosion, kaboom, and then gets pushed back down.
Keeps pushing it and pushing it.
Mm-hmm.
We already did inflating tires. The more gas, more air I pump into the tire, the more the tire fills.
So let's do some calculations.
Okay. So first things first, you need to know these need to be in Kelvin. There's no change in temperatures, so that's not going to work. Got to be in Kelvin. The other units can vary, but let's just make sure that they're the same on both sides: atmospheres, pascals, anything for pressure. Okay. So first one, I got a sample of gas at 273. Monica's going to write down our equation, and we're going to start plugging and chugging. 273 kelvins, 5 atmospheres is pressure, 150 milliliters is volume. These are my initial conditions. I know that they're my initial conditions because it says the volume is decreased to. So now that's going to be my final volume and my final pressure, and then we'll have to calculate this new temperature. Okay, so we're just going to plug and chug. We're going to plug in the first 3 variables on the left side. 5 times 150 divided by 273. And on the final side, I got 100 times 3 divided by T2. And we will just be able to do our algebra skills to solve for the one variable. Like Monaco said, we'll always be given 5 variables, solve for the 6th. Okay. And there is an equal sign, so guess what we get to do? We get to cross multiply and follow all of your rules of algebra to solve for that unknown.
Next.
Good. Erase we go. New problem. New problem. I'm just going to find now what is the final volume. So again, same equation. My initial conditions are the first 3, and that isn't always the case, but that's just how it reads. I have a gas that's at these conditions. What will the new volume be is the next piece, so I know that that is the final. Okay, so that reading comprehension piece we got to get good at. We got to know that liters and milliliters are volume. K is temperature, and atmospheres is pressure. So we need to be able to put the right pieces into the right places. I got 2 times 4 over 346 equals 1 times x over 273. The x is in a different place, but we're still going to cross multiply, do what we need to do to get x by itself, and remind me in class, I will teach you a trick to go even faster than cross multiplication can do for you.
I won't.
Okay.
I'm going to do it the old school way.
You do it the old school way. I'm going to go fast because I do my math fast. Visca wants us to do it fast, right, guys?
Fast math. That's what he's
Fast
all
math.
about.
I don't know, but I want to do it fast because I want to save time. So this one I like a lot because it says 200 or 20 milliliters of gas at STP. So we need to make sure we review that and know what STP means. It means 0 degrees Celsius, which converts into 273 kelvins and 1 atmosphere. And then it's heated to 398 kelvins. What is the final pressure if the volume is 100? So I know the final, I'm looking for final pressure. I'm given final volume. Heated 2 is the change in temperature. So I have my final temperature, plug and chug. I got 1 times 20 over 273 equals 100 times x over 398. Again, plugging and chugging. We're not giving you the answers. We expect to see that you can come up with these answers on your own and check when you get to class.
Yeah.
Okay.
And that really sums it up, I think,
That
right?
is it. So you got some practice pages to do and
Done with the unit.
done with the unit. See you.
Hasta la vista, baby.